Hello everyone, and welcome back to our series on quantum mechanics. In the last video, we introduced the famous Schrödinger equation as a way of describing how quantum states evolve in time with respect to a given Hamiltonian. In this video, we will continue our discussion of the Hamiltonian by talking about the role that symmetries play in computing energy eigenstates. The first thing you may be wondering is what a symmetry is. Well, before we can discuss that, we first need to define symmetry operations, which are basic geometric manipulations that we can perform. I'm sure you've probably heard of these before. One example of a symmetry operation is translation, where we simply take an object and move it from one position to another. We usually characterize this translation by the vector describing the displacement of the object from its initial to final position. Another typical symmetry operation is reflection, where we simply take the mirror image of an object across a line, plane, etc. We also have the inversion operation, which reflects an object through the origin, taking the coordinates of each point and negating them. Lastly, we also have rotations, which in 2D are about a given point, but in 3D are about a specific axis. Of course, we can define many other types of symmetries as well, beyond those listed here. Generally, these symmetries are quite closely connected to group theory, which we will discuss later on when it becomes relevant. Among all the transformations presented here, there's one common trait that they all have. They leave the shape of the object itself invariant under the transformation, meaning that all we change is the position and orientation. If we consider a symmetry operation applied to something like the wave function, all this means is that the norm remains unchanged. Consequently, we have that a symmetry operator is simply a unitary operator and vice versa. Altogether, we have that a given symmetry means that an object is invariant under such a transformation. Now, why do we care about symmetries? Well, there are many cases in which we will be analyzing Hamiltonians that exhibit particular symmetries that we can use to find their energy eigenstates more easily. More generally, suppose that we have a Hermitian operator Q that is invariant under a given symmetry. This means that applying Q and then undoing the symmetry operation gives us the same result as just applying Q on its own. Rearranging this gives us that QU equals UQ, meaning that this condition holds if and only if U and Q commute. In other words, we have that H is invariant under a symmetry transformation U if and only if the commutator of U and Q is 0. We now can use the fact that we discussed in a previous video to also conclude that this implies that U and Q share a complete eigenbasis and vice versa. In other words, there exists a basis of eigenvectors for U for the whole Hilbert space that are also eigenvectors of Q. If the eigenvalues are non-degenerate, this means that the eigenvectors of U are exactly eigenvectors of Q. If the eigenvalues are degenerate, then there's always a choice of complete eigenbasis, which consists of eigenvectors of both U and Q, though not every eigenbasis for the operator with the degenerate eigenvalues may be an eigenbasis for the other. Consider what happens if we have Q as the Hamiltonian operator. This means that if the Hamiltonian is invariant under a given symmetry transform, then assuming a non-degenerate spectrum, we can simply take the eigenvectors of the symmetry to also be eigenvectors of the Hamiltonian. If the spectrum of one of the operators is degenerate, for instance, maybe the Hamiltonian has multiple stationary states of the same energy level, then there exists a choice of eigenbasis for H that is also an eigenbasis for U, though not every eigenbasis for H is also an eigenbasis for U. However, if U is still non-degenerate, then the eigenbasis for U is always an eigenbasis for H. As an example, consider the parity transform P, which effectively behaves as the inversion transform described previously. Let us consider what happens if the Hamiltonian commutes with the parity operator. Since applying the parity transform twice leaves the state unchanged, we have that P squared is simply the identity. Hence, the eigenvalues of P must be plus or minus 1. An eigenvalue of 1 means that the eigenfunction is unchanged when x is swapped with minus x. In other words, this means that the eigenfunction is even. Similarly, an eigenvalue of -1 implies that the eigenfunction is odd. Consequently, we have the eigenstates of p corresponding to plus and minus 1 are even and odd functions, respectively. Consequently, if p commutes with h and energy levels are not degenerate, then the energy eigenstates of h must be composed entirely of even and odd functions, or in the case of degenerate energy levels, can be represented as odd and even functions. Physically, you may be wondering what p commuting with h really means. Well, if we evaluate the commutator of the two using a test function, we find that the kinetic energy operator always commutes with p. For p to commute with v, we find that v of x must equal v of minus x, meaning that v has to be an even function. In other words, if the potential is symmetric about the origin, we have that the energy eigenstates are even and odd functions. And by symmetric in this case, I mean that the potential is even. And vice versa for non-degenerate spectra. This is useful to keep in mind as a sanity check going forward. If you compare observables and symmetries, you might notice that they share some peculiar similarities. In particular, looking at their eigenvalue and eigenstate properties, we can see that they both have orthonormal eigenstates, with the only difference being that observables have real eigenvalues and symmetries have eigenvalues that lie on the unit circle, which I denote here as t. However, we can map values on the real axis to values on the unit circle in a continuous fashion using this complex exponential map. Note that the choice of sign in the exponent is really a matter of convention. In particular, this means that for any observable q, by Sylvester's formula, we can define a corresponding group of symmetry operators u parameterized by alpha defined as follows. We also add this additional 1 over h bar factor in the exponent by convention in Qm. And when we normally work with groups in pure math, we do not have such a factor. In group theory, this observable is referred to as the infinitesimal generator for the continuous group U of alpha. Note that we can relate an infinitesimal generator and the continuous group it generates via the following relations. As an example, consider the symmetry operation generated by the momentum operator, which is given as follows. Note that I have replaced alpha with x naught here for reasons that will soon become clear. To understand what the symmetry actually does, let's apply it to a wave function psi in the position basis. Expanding out this exponent, we get that this exponential becomes an exponential of a derivative scaled by this value x naught. If we now Taylor expand the exponential, we get the following expression. Note that if psi is analytic, as we assumed, this simply reduces to a Taylor expansion of psi about x evaluated at x minus x naught, giving us the following. Hence, we have that the momentum operator generates a translation operator that shifts the position of a particle to the right by x naught. As you might expect, we can also define a momentum shift operator generated by the position operator, though the sign of the actual shift in this case ends up flipping. You also might realize that the Hamiltonian operator actually generates the time evolution unitary described in the previous lecture. Unlike with position and momentum, however, it is not possible to generate energy shifts by treating time as an observable and generating a symmetry from this. I won't go into the arguments as to why this is the case, but as the explanation is pretty involved, but just keep this in mind. Altogether then, we have that momentum generates position shifts or translations. Position generates momentum shifts, and the Hamiltonian operator generates time shifts. Okay, so we can transform the wave function intuitively using these generators, but what else can we do with this information? Well, consider our previous discussion involving shared eigenstates. If a given symmetry commutes with the Hamiltonian, we can use this relation with the generator to show that the generator also commutes with the Hamiltonian. This relationship also holds the other way around as well, trivially, using the Taylor expansion of the symmetry operator. In particular, this means that if a Hamiltonian is invariant under a given symmetry generated by an observable, it shares a complete set of eigenstates with the observable that generates the symmetry. If a given observable also commutes with the Hamiltonian, it also implies that it is conserved, as the coefficients of the energy eigenstates, which are also eigenstates of this observable, remain unchanged except for phase as the state evolves through time. This is simply a quantum version of Noether's theorem from classical mechanics. Let's see this technique applied in practice. Consider a free particle, meaning that the potential is zero everywhere. Since the Hamiltonian has no position dependence, we have that shifting the position of the particle leaves the Hamiltonian invariant. Consequently, since the Hamiltonian is invariant under translation, we have that momentum is conserved, and the energy eigenstates are simply momentum eigenstates. This means that the energy eigenstates for v equals 0 are simply plane waves, which makes sense intuitively, since you may already know that the energy of a plane wave is related to its momentum as follows. All of these results can also simply be derived by just using the fact that the Hamiltonian of a free particle is given as follows, and then solving the resulting TISE, or using the fact that p squared over 2m has the same eigenstates of p. Note that in general, translation symmetry doesn't really hold for any potential except for the free particle, or any constant potential, since any kind of position dependence means that the Hamiltonian cannot possibly remain unchanged under every possible shift. This is not to say that there are non-Hamiltonians that are unchanged under certain fixed shifts. However, the free particle is the only one invariant under all such shifts, meaning that it is the only potential for which the energy eigenstates have fixed momentum. One thing you might have noticed is that any constant potential is even, meaning that this Hamiltonian is invariant under parity transforms. Consequently, we should expect the energy eigenstates to be even and odd functions. However, as we have currently defined them, this is not the case. However, remember that these eigenstates are degenerate, as both e to the ikx and e to the minus ikx are eigenstates with energy h bar squared k squared over 2m. Consequently, we can take linear combinations of these eigenstates to obtain other eigenstates with the same energy. In particular, if we add and subtract these states and then divide them by 2, introducing a factor of I in the sine case, we can get that these become cosine of kx and sine of kx, which both pertain to the same energy level but are also parity eigenstates, as cosine of kx is even and sine of kx is odd. Note that even though parity and momentum commute with the Hamiltonian, they do not commute with each other. Consequently, based on this fact alone, we actually have that for H to share a complete eigenbasis with each operator, H must have a degenerate spectrum. This fact holds in general for any two operators that commute with H and do not commute with each other. As a brief aside, you might be wondering how we time evolve a wave packet in free space. After all, in the previous video, we only discussed how to time evolve a state where the Hamiltonian has a discrete energy spectrum. Furthermore, our eigenstates are no longer bound states here and are unnormalizable. Well, as it turns out, we can simply use the same procedure as before, simply replacing the sum over energy eigenstates with an integral parameterized by some quantity psi, which the energy is a function of. In our case, we have that psi is simply p, giving us the following expression for psi of xt, in terms of the momentum wave function psi hat of p0, which is obtained by transforming the position wave function at time t equal to 0 into the momentum basis. Altogether, we discussed how symmetries can be used to deduce various properties about energy eigenstates, without having to actually compute them directly. This technique is somewhat trivial for the 1D wave functions, as the symmetries we work with are not exactly very useful. However, we can later see how useful this technique can be when working with 3 dimensions, especially when we're working with spherically symmetric potentials. In the next video, however, we will begin our next section of QM by explaining how to compute the energy eigenstates for various important 1D potentials and explaining their interesting properties along the way. I hope you enjoyed this video, and I'll see you next time.